Something is happening 484 million miles from Earth, and nobody is telling you the full story. NASA's most advanced spacecraft are circling worlds that shouldn't exist by any rule of science we thought we understood. Beneath frozen shells of ice, there are oceans. Beneath those oceans, there may be life. On a moon drenched in fire, a volcano just erupted with 6 times the energy of every power plant on this entire planet combined. And the most shocking part? This is not a theory. This is not speculation. This is happening right now, and humanity is only beginning to understand what it means. There is a moment in every great investigation when the evidence stops being interesting and starts being terrifying. Not terrifying in the way a threat is terrifying. Terrifying in the way a revelation is, when something you thought you understood reveals itself to be something far larger, far stranger, and far more consequential than anything you had imagined. That is the moment NASA is living right now. That is the moment the entire scientific community is quietly processing. And that is the moment this story begins. Jupiter, the largest planet in our solar system, is orbited by a staggering 95 known moons. Most of them are small, unremarkable rocks locked in gravitational orbit around a gas giant so massive it generates its own internal heat. But 4 of those moons are different. 4 of those moons have forced planetary scientists to rewrite the rulebook on where life can exist in the universe. These 4 moons, Io, Europa, Ganymede, and Callisto, are known as the Galilean moons, named after the astronomer who first observed them through a crude telescope in 1610. What Galileo saw were 4 dim points of light orbiting Jupiter. What NASA is seeing today is something that would have been considered science fiction 20 years ago. Think about what that means. 400 years of looking at these objects as distant curiosities. 400 years of assumptions. And in just the last few years, everything has changed. Let's start where the story is loudest. Let's start with fire. Io is Jupiter's 3rd largest moon and the most volcanically active world in our solar system. That sentence does not carry the weight it deserves when you read it the first time. Let it sit for a moment. The most volcanically active world in our entire solar system. Not the most active on a short list of interesting candidates, the most active among every single planet, moon, asteroid, and body we have ever observed across billions of miles of space. And NASA's Juno spacecraft has been flying directly through that chaos, getting closer than any machine in history. And what it found in December 2024 shattered even the most extreme expectations scientists had built over decades of observation. Scientists with NASA's Juno mission discovered a volcanic hotspot in the southern hemisphere of Jupiter's moon Io. The hotspot is not only larger than Earth's Lake Superior, but it also belches out eruptions 6 times the total energy of all the world's power plants. Read that again. 6 times the combined output of every power plant on the entire surface of this planet. Every nuclear reactor, every coal plant, every wind turbine, every hydroelectric dam combined, and then multiplied by 6. That is the scale of what Juno observed on a single volcanic feature on a moon that fits comfortably within the continental United States. And here is where it gets worse. That eruption, the most energetic in Io's history, identified by Juno on December 27, 2024, was still firing out lava and ash as recently as March 2, 2025. This was not a brief geological event. This was not a spike in readings that scientists could file away as an anomaly. This was a sustained, continuous eruption of incomprehensible power, stretching across months, still burning, still building, still defying every scale we use to measure geological violence. And Juno kept watching. Even by the standards of Io, the most volcanic celestial body in the solar system, recent events observed on the Jovian moon are extreme. That quote came directly from NASA's own scientists, people who study Io for a living, who have spent careers cataloging its eruptions and mapping its tortured surface, looked at what Juno captured, and described it as extreme. When scientists who study the most violent geological world in the solar system use the word extreme, that is not casual language. That is a signal. But here is where the story turns from spectacle into science. Because the Juno mission was not just photographing the surface of Io, it was going beneath it. Scientists with NASA's Juno mission discovered that the volcanoes on Jupiter's moon, Io, are each likely powered by their own chamber of roiling hot magma, rather than an ocean of magma, solving a 44-year-old mystery about the subsurface origins of the moon's most demonstrative geologic features. For over 4 decades, scientists had debated what exactly was driving the relentless volcanic fury of Io. The leading theory for much of that time was that a global magma ocean beneath the surface was the fuel source, one massive interconnected reservoir of molten rock feeding every eruption simultaneously. Juno dismantled that idea entirely. Each volcano has its own engine, each eruption has its own source. What that means is that Io is not a world sitting on one catastrophic ticking bomb. It is a world with hundreds of individual catastrophic ticking bombs, each one independent, each one capable of what we observed in December 2024. And this is where everything changes. At Ganymede and Europa, Juno explored tens of miles below the surface, assuming their ice shells were mostly pure water. But the ability to probe into the volcanic rock at Io was an unexpected discovery. That line from NASA scientist Scott Bolton is critical to understand, because the same instrument that was taking the temperature beneath the surface of Io, the microwave radiometer that reads heat signatures through rock and ice, was also being turned toward Europa and Ganymede. The same technology, the same spacecraft, the same mission. And what it found under those frozen shells is what brings us to the deeper part of this story. We need to talk about Europa, and we need to talk about it carefully, because what is being said about this moon in scientific circles right now is extraordinary. Not in the way science press releases are usually extraordinary, breathless, exaggerated, designed to generate funding. Extraordinary in the way that informed sources working at the highest levels of planetary science are choosing their words with unusual precision, as if they are afraid to say what they actually believe because of how significant it would be. Scientists believe that beneath Europa's thick layer of ice, estimated to be between 15 and 25 kilometers thick, lies a vast saltwater ocean that could harbor conditions favorable for life. Recent findings suggest it may hold more water than all of Earth's oceans combined. Pause on that. More water than all of Earth's oceans combined, on a moon that most people cannot even locate on a diagram of the solar system. A moon that is slightly smaller than Earth's own moon. A moon that, from the outside, looks like a cracked billiard ball, its surface sliced by thousands of intersecting ridges and fractures. But beneath that cracked shell, there is more liquid water than exists anywhere else in the known solar system, and NASA has sent its largest planetary mission ever to go find out what is living in it. In 2024, NASA launched the Europa Clipper mission. It's the largest spacecraft NASA has ever used for a planetary mission. It will travel 2.9 billion kilometers and reach Jupiter by 2030. This is not a small robotic explorer on a budget mission. This is a $5.8 billion spacecraft the size of a basketball court, equipped with 9 instruments, built specifically to ask one question that humanity has been wrestling with since the first time someone looked at the stars and wondered if we were alone. The Europa Clipper is not a life detection mission. NASA is careful to say that publicly, measured and precise about the language, but read between the lines of what the instruments aboard that spacecraft are designed to do, and the question becomes unavoidable. The Clipper orbiter will conduct a detailed survey of Europa's surface, deep interior, thin atmosphere, subsurface ocean, and potentially even smaller active vents. Clipper will try to take images of any plumes and sample the molecules it finds in the atmosphere with its mass spectrometers. It will also seek out a fruitful site from which a future Europa lander could collect a sample. A future lander. Scientists are already thinking beyond the Europa Clipper, already planning the next step, already identifying the site where a robotic probe might touch down and drill through the ice and descend into the ocean below. We are not decades away from that conversation. We are having it now. But here is what most people are not seeing. Europa is not the only ocean world in this system, and that is where this story becomes something even the scientists are struggling to fully process. Jupiter's moon Callisto, long regarded as a frozen, crater-ridden celestial body, is now at the center of an exciting scientific breakthrough. New research strongly suggests that beneath its icy exterior lies a vast subsurface ocean, a discovery that could redefine our understanding of this distant moon and its potential for habitability. For decades, Callisto was the moon scientists essentially ignored. It was ancient, battered, unchanged. Its heavily cratered surface was read as evidence that nothing had ever happened there, that no internal heat had ever reshaped it, that no geological process had ever renewed it. It looked dead because scientists assumed it was dead. But in early 2025, a new analysis of magnetic field data turned that assumption completely on its head. In the 1990s, NASA's Galileo spacecraft flew past Callisto and gathered magnetic field data that hinted at something unexpected, a possible subsurface ocean beneath its icy crust. That hint sat in the data for nearly 30 years, partially understood, partially dismissed, overshadowed by the more dramatic signals coming from Europa and Ganymede. But when researchers in 2025 ran a multi-frequency investigation of Callisto's induced magnetic field, essentially probing the moon with electromagnetic signals at multiple wavelengths to read what was generating the response, the answer became difficult to argue with. There is salt water beneath Callisto, a liquid ocean on a world that looked completely dead from the outside. This is not chaos. This is a pattern. Think about what the pattern means. We are not looking at one or two unusual exceptions. We are looking at a system where ocean worlds appear to be the rule, not the exception. Where liquid water hidden beneath miles of ice and rock is not a planetary curiosity, but an architectural feature of the Jovian neighborhood, where the conditions that scientists once considered the minimum threshold for life, liquid water, chemical energy, the right chemistry, appear to exist simultaneously on at least 3 of Jupiter's 4 largest moons, possibly all 4, and the implications of that do not stop at Jupiter. Now, let's talk about Ganymede, because Ganymede breaks the rules in a way that none of the other moons do. Ganymede breaks the rules in a way that nothing else in our solar system does, with the exception of Earth. Ganymede is the only moon known to have its own magnetic field, a discovery made by NASA's Galileo spacecraft in 1996. The magnetic field causes auroras, which are ribbons of glowing, hot, electrified gas in regions circling the north and south poles of the moon. A moon with its own magnetosphere, a moon generating its own electromagnetic shield, independent of Jupiter's overwhelming magnetic environment. That alone would make Ganymede one of the most fascinating objects in planetary science. But there is more. Ganymede hides an ocean 100 kilometers deep, with 9 times more water than Earth's seas. 9 times. Not slightly more water than Earth. Not comparable amounts. 9 times. A body of liquid salt water beneath Ganymede's icy surface so vast that if you could somehow drain all of Earth's oceans and compare them to what sits beneath Ganymede's crust, Earth's contribution would be less than 12% of the total. And that ocean is sandwiched between layers of ice and rock, pressurized, insulated from the absolute cold of space, warmed from below by tidal forces so powerful they squeeze the moon's interior like a hand closing slowly around a piece of fruit. Scientists now have firm evidence that Ganymede, like Europa, conceals an ocean under its icy shell, one that may contain more water than all surface water on Earth combined. The ESA's JUICE mission, the Jupiter Icy Moons Explorer, is already in transit to conduct the first ever orbital investigation of Ganymede. But that arrival is still years away. JUICE will focus on Ganymede, the only moon with its own magnetic field, while Europa Clipper will conduct detailed flybys of Europa. Both missions will investigate how these moons interact with Jupiter's intense magnetic environment and study tidal forces that may sustain subsurface oceans. For the first time in history, 2 major space agencies, NASA and ESA, are coordinating simultaneous missions to the same system, each targeting different moons, combining their data in a scientific operation of unprecedented scale. That level of coordination does not happen for routine exploration. That level of coordination happens when the stakes are high enough to justify it. And there is one more development that the mainstream science coverage has not given nearly enough attention. Something that changes the entire framework through which we should be reading all of this. Before NASA's Juno mission, 3 of Jupiter's 4 largest moons, Io, Europa, and Ganymede, were shown to produce distinct auroral signatures in Jupiter's atmosphere. But Callisto, the most distant of the Galilean moons, remained a mystery. The auroras above Jupiter's poles are among the most powerful electromagnetic displays in the solar system. And the Galilean moons leave marks in those auroras, electromagnetic footprints, signatures written in light, and radiation in the upper atmosphere of the gas giant. Scientists had confirmed 3 of the 4 moons were leaving these marks. Callisto was the one they could not find. And then Juno found it. Juno detected Callisto's auroral footprint. The last missing piece in a puzzle that now shows all 4 of Jupiter's largest moons are electrically connected to the planet they orbit, each one tugging on the magnetic environment of Jupiter in a unique way. Each one branded into the planet's atmosphere like a fingerprint. This is not just a data point. This is a window into the mechanics of a system that is far more interconnected, far more dynamic, and far more active than anyone fully appreciated even a decade ago. What most people are not seeing is how all of this connects, not as isolated discoveries about individual moons, but as a coherent picture of a system where the physics that create the possibility for life are operating on a scale we are only beginning to measure. The tidal forces that heat Io to volcanic fury are the same class of forces that maintain the liquid oceans beneath Europa, Ganymede, and Callisto. Jupiter is not just a planet, it is a furnace that powers its entire neighborhood. It is the gravitational engine that kneads its moons like dough, generating heat in their interiors, keeping their oceans liquid, sustaining chemical gradients that could, in theory, and increasingly in evidence-supported theory, drive biology. According to informed sources within the planetary science community, the questions being asked in private are sharper than what appears in press releases. The public language is careful, measured, designed to manage expectations, but behind closed doors, at conferences, in the margins of papers being peer-reviewed right now, the conversation is more direct. If life exists anywhere beyond Earth in our solar system, the Jovian system is the most probable address. Europa Clipper is a $5.2 billion mission designed to investigate whether Europa's subsurface ocean contains the necessary ingredients to support life. Upon arrival, it will conduct 49 close flybys of Europa, skimming as low as 16 miles above the moon's icy surface. 16 miles. At those altitudes, the spacecraft will be close enough to sample the chemistry of Europa's thin atmosphere, to detect any plumes of water vapor rising from the surface, to read the composition of the material erupting from cracks in the ice. If organic molecules are there, the Clipper's instruments will find them. If the chemistry of life's building blocks is present in the plumes or the surface frost, the data will show it. And whatever the data shows, it will arrive on Earth sometime after 2030 and will belong to a category of scientific findings that humanity has never encountered before. The real story here is not any single discovery. The real story is the acceleration. The rate at which the Jovian system is revealing itself is increasing in a way that was not predicted even 10 years ago. Juno was designed primarily to study Jupiter's atmosphere and interior structure. It has exceeded that mandate so dramatically that NASA has extended the mission repeatedly, redirecting the spacecraft to fly closer to the moons, tasking it with answering questions that were not on the original scientific agenda, because those questions became too important to ignore. The technique Juno uses is novel in that each wavelength explores different depths, providing a new way to characterize the deep atmosphere of giant planets and the subsurface crusts of icy and rocky moons. A tool designed to study one thing is discovering new things at every pass. That is how fast the science is moving. That is how quickly the model of the system is being rebuilt. And then there is the timeline. Europa Clipper's journey to Jupiter began with its October 2024 launch. A swing past Mars in early 2025 accelerated the spacecraft, followed by an Earth encounter in December 2026, with the final gravitational slingshot pushing the spacecraft out to Jupiter, arriving in April 2030. We are currently in that window. As this script is written, Europa Clipper is somewhere between Mars and Earth, coasting through the inner solar system, instruments being tested and calibrated, teams on the ground refining their observation strategies for the moons it will explore. JUICE is making its own long crossing, set to arrive at Jupiter in July 2031, where it will begin one of the most ambitious moon tours in space exploration history. Both spacecraft are in transit right now. Both missions are live. The clock is running. But here's the thing about timelines in science that most coverage gets wrong. The discoveries do not begin when the spacecraft arrives. The discoveries have already begun. They are happening now, with Juno still orbiting, still flying, still uncovering. Juno's mission is one of continuous discovery. As mission principal investigator Scott Bolton has said, one of the great things about Juno is its orbit is ever-changing, which means we get a new vantage point each time as we perform a science flyby. In the extended mission, that means we're continuing to go where no spacecraft has gone before, including spending more time in the strongest planetary radiation belts in the solar system. Every orbit, a new angle. Every flyby, a new data set. Every data set, a new revision of everything we thought we knew. What that means in practice is that the picture, consider the broader stakes for a moment. The question of whether life exists beyond Earth is not merely a scientific question. It is a philosophical one. It is a theological one. It is a question that sits beneath every civilization's understanding of its own significance. If Europa's ocean contains microbial life, the implications are not limited to biology. They extend to every framework through which humanity has ever understood its place in the universe. The discovery of even the simplest organism beneath Jupiter's ice would mean that life is not a planetary accident. It would mean that wherever the conditions are right, life emerges. And if life emerges wherever the conditions are right, then a universe filled with billions of planets and moons with liquid water becomes something altogether different from a vast, empty void punctuated by one inhabited rock. Biosignatures indicative of habitability. Biosignatures. That word, now appearing regularly in mission planning documents and peer-reviewed papers, carries enormous weight. It is the language scientists use when they are no longer discussing the possibility of habitability in abstract terms, but are actively identifying targets where the evidence of life, if present, might be detectable. We have crossed a threshold. We are no longer asking whether these moons could support life in theory. We are designing instruments to look for the fingerprints of life and pointing them at specific coordinates on specific moons in a specific system. What excites scientists most is the possibility that zones of frozen waters from Europa's subsurface ocean might upwell because of icy crust tectonics, and that the presence of these materials in places where the crust appears to be thin or active, as revealed by Europa Clipper instruments, could reveal the composition of the ocean and whether it could possibly support life, and help guide the decision on where to put a potential future Europa lander to search that material for evidence of life. A Europa lander, after the Clipper, after the data, after the identification of the optimal site. Scientists are already thinking in terms of follow-on missions that haven't been funded yet, that won't fly for decades yet, because the momentum of what is being discovered is already pulling the scientific community forward faster than the institutional timelines of space agencies can comfortably accommodate. And meanwhile, Io keeps burning. Plumes rising hundreds of miles above the surface, painting Io in shades of yellow, orange, red, and white that make it look like a pizza made by a geologically unhinged deity. This is not a moon in crisis. This is a moon in its natural state, and Juno has been sitting in the front row watching. Is tearing Io apart from the inside, is keeping the oceans beneath the icy moons from freezing. Jupiter is simultaneously the destroyer of one world and the life support system of three others. That is not a metaphor. That is the physics of the system as we currently understand it. What informed observers are paying close attention to now is not just the science. It is the institutional response. The fact that NASA launched its largest planetary spacecraft in October 2024, specifically to study one moon's potential for life, is a statement. The fact that ESA designed an entire flagship mission around the Jovian system and is currently in transit is a statement. The fact that both agencies are formally coordinating their efforts, planning joint observations, sharing data frameworks across international scientific teams is a statement. Institutions of this scale, with budgets of this magnitude, do not make commitments like this to questions they consider unlikely to yield significant answers. They invest at this level when they believe the signal is real. As Europa Clipper project scientist Robert Pappalardo has said, we are at the threshold of a new era of exploration, a mission that will help us learn how common or rare habitable environments are beyond Earth. Common or rare? That framing is everything. Not whether habitable environments exist, how common or rare they are. The scientific community's working assumption has already shifted. The question is no longer, does this happen anywhere else? The question is, how often does this happen, and what are the implications of the answer? What we are witnessing is not a series of interesting press releases about distant moons. What we are witnessing is the methodical, instrument by instrument, flyby by flyby, dismantling of one of the most fundamental assumptions humanity has held about the universe, that we are uniquely positioned to exist. That life, at least complex life, perhaps even simple life, is so extraordinary a phenomenon that it could only emerge under the specific and improbable circumstances that gave rise to our own pale blue dot. That assumption is being tested right now with hardware that cost billions of dollars and took decades to design in the most consequential scientific investigation in human history. And we will not have the answer for years. That is the thing about science at this scale. The missions are slow, the data takes time, the analysis is careful, the peer review is rigorous. Results are not announced until they are verified, and verified again, and then debated, and then refined. By the time Europa Clipper completes its 49 flybys and returns the full data set, we will be in the 2030s. By the time JUICE finishes its orbital survey of Ganymede, we will be approaching the mid-2030s. By the time a lander, if funded and built, reaches Europa's surface, we are talking about the 2040s at the earliest. So here is what remains unresolved, and what should stay with you long after this script ends. We know that beneath the ice of Europa, there is a liquid saltwater ocean holding more water than all of Earth's seas. We know that Ganymede, the largest moon in the solar system, the one that generates its own magnetic field, has a subsurface ocean 9 times the volume of Earth's. We know that Callisto, the moon everyone had written off as dead and irrelevant, is now showing signs of the same hidden ocean architecture. We know that Io is erupting with a power that exceeds the combined output of every energy source on our planet by a factor of 6, and that the same gravitational engine driving those eruptions is what keeps the other moon's oceans liquid. We know that NASA and ESA both have spacecraft in transit to investigate these worlds in detail, that the scientific community is already thinking about landers and sample return missions, and that the word biosignature now appears without embarrassment in peer-reviewed discussions about these moons. What we do not know is what Europa Clipper will find when it skims 16 miles above Europa's surface in 2031 and opens its mass spectrometers to sample what is rising from the cracks in the ice. We do not know what JUICE will detect when it begins its orbital survey of Ganymede and turns its ice-penetrating radar toward the deep subsurface. We do not know whether the chemistry of those hidden oceans will be sterile, or whether it will carry the signatures of something more. We do not know whether in the 2030s or 2040s, a lander sitting on the surface of Europa will drill through the ice and descend into a global ocean and return data that forces the entire human species to reckon with an answer it has been approaching for 400 years. What we do know is this: the investigation is live, the spacecraft are moving, the instruments are being calibrated, the scientists are watching, and somewhere out there, 484 million miles from Earth, beneath miles of ice and above a rock-strewn seafloor bathed in tidal heat, the most important question humanity has ever asked may already have an answer. We just have not reached it yet, but we are closer than we have ever been. And the next few years will determine whether what we find out there will change everything we thought we knew about the universe we live in, or whether the silence will simply grow deeper and stranger and more difficult to explain. Either way, nothing about this story is finished, not even close.